Good morning, everyone. So we're going to continue today in chapter 6. Before we get started, I wanted to mention for midterm 3 next week, the equations that you'll get with the exam, you'll get a chance to see those when we open up the practice exams. So you'll get a chance to see that sample info booklet that you'll get with the exam. For whatever reason, they primarily only put the chapter 6 equations onto, I'm going to make sure not to confuse. Chapter 6 equations are on the little sheet that you'll get with the scratch paper booklet. And for whatever reason, they put the chapter 5 equations into like a question on the exam. So like everybody's first question on the exam will have a bunch of chapter 5 equations. And the equations you get will effectively be the end of chapter summarized equations. So if you go to the end of chapters 5 and end of chapter 6 and look at the equations that they kind of summarize, those are the equations that you'll see on the test. And like I said, with the practice exams, you'll get a chance to see what those look like in the form that you'll see them at on the real exam. So just think about when the Carmen exams come up, that you can look in the module, you'll see the sample info booklet, and then also that first question of those exams will have the equations that we're talking about, so you can see them what they'll look like on the real exam. Okay, so getting back into chapter 6, for the H atom we saw, for having one electron within our atom, we were able to very easily or possibly calculate the difference of energy from its ground state. The lowest energy level we saw was n equals 1 for the H atom. And then we could calculate the energy between n equals 1 and 2, n equals 1 and 3, 1 and 4, 1 and 5. And we saw that 1 to 2 had a big difference of energy, then up to 3 was a little bit higher, up to 4 is just marginally a little higher, 5, 6, etc. higher, and then up to infinity was kind of where we were maxing out. As n approaches infinity is the idea that the electron is now being lost from the atom. The idea of going from n equals 1 to 2 to 3 to 4 is pushing the electron further and further away from the nucleus. As soon as n approaches infinity, that's where the electron's been removed or ionized from the atom. Now, for a system with one electron, it's possible to have the precision and the ability through equations to calculate the energy differences between that ground state n equals 1 and those excited state, those higher energy states. But for other atoms, it becomes a little bit trickier to work out through any kind of equations what the difference of energies would be between their ground states and their excited states. So what becomes more, the question is then, well, can we understand what the ground states are? Can we understand where the electrons are in our multi-electron atoms with some degree of just thinking about where the electrons are going to reside, what type of orbitals they might reside in? And the whole concept of thinking of, instead of an electron being somewhere spinning around the atom, maybe here, 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 instead of thinking of it as a discrete particle, we tend to think of the probability of like a n equals 1 electron in a hydrogen is it has some probability around the nucleus of that atom that's like, say, spherically symmetrical around that atom. And then if you go to n equals 2, it's just the probability distribution is a little further away. N equals 3, even further away. And so we start to think in probability distributions, and that's because of what we saw. One, the electron's behaving like a wave, so the electron's more of a wave particle than it is just a particle. And then it's also, we're limited by the uncertainty principle. So if any given moment we want to know where the particle is, we kind of have a fuzzy understanding of how well we can understand or calculate the velocity at that point. So it kind of gives us like an idea that when we try to see an electron, we just see like almost like a distribution or a probability distribution for where that electron is. And so as we get into multi-electron atoms, we look to quantum mechanics, which gives us these things we call quantum numbers that kind of helps us see how the space is kind of like chunked out around an atom for electrons to distribute into. And so let's look at these quantum numbers, kind of what they mean, and then how they're limited by the possible range of values that kind of begin with the n value having whole number values starting from 1. So the n value, we call that the principal quantum number, is the n quantum number. This is the one we saw from the Bohr model, and it's relating to the size of the orbital. So as n increases, the size of the orbital increases. So n can take on values from 1, 2, 3 on upward, just in whole number values. And so n can't be 0, so the lowest n can be is 1. So the thought of n equals 0 would be that's the electron somehow collapsing into the nucleus, which isn't something that, like, we know H atom exists with that one electron, not collapsing into the nucleus. And so then a second quantum number that we talk about or can find from quantum mechanics is the angular momentum quantum number. This is symbolized by the letter L. And so this is telling us something about the shape of the orbital. And so when we're thinking about the H atom, we're kind of just thinking almost like a sphere in terms of where the electron is. And so that's the shape of an orbital when L is equal to 0. So L equals 0, we call that an S shape. You may have seen an S orbital before. And L equals 1 is a P shape. And L equals 2 is a D-shaped set of orbitals. L equals 3 is an F shape. If we go to L equals 4, it would be a G shape. L equals 5, an H shape. You just kind of go after N equals 3, you just go alphabetically up in terms of the shape of the orbitals. But the actual, like these designations here aren't so important. What's going to be more important is us to think about what it's going to look like to have an L value 0 versus 1 versus 2 versus 3. What this L value is it's telling you something about what we call either angular or planar nodes. So, and that is like a node or a plane that will go through the nucleus of the atom. And so if you think of an S orbital having none of those nodes, that's why the S orbital just kind of looks like an orbital that looks like a sphere. And there's shapes on a later slide too, so you don't necessarily have to see all the shapes that we're showing here. So we'll come back to kind of what different orbitals look like in a few slides from now. But the P-shaped orbital, if we're going to have this being the nucleus of the atom, we're going to have like a plane extending through that atom where there's going to be no probability of finding an electron. And so then if that's the case, then our orbital has to kind of look like a P shape. And so then the shading of our orbitals is showing us where the probability is the highest. So we have a higher probability being further away from the nucleus, and then towards the nucleus, like really light shading or no probability of finding the electron. And so we get like lobes because that little like nodal point in the middle is a point of 0 probability of finding an electron that extends through the plane of the nucleus of that atom. And so that's our P shape, that's the L equals 1 type shape. And then the L equals 2 type shape is our D shape set of orbitals. And so if you have a nucleus and then you have sort of like 2 planes going through the atom where you have no probability of finding an electron, then you start to have like 2 sets of lobes. So you have orbitals that kind of start to look like double clover leaves. And it's just this orbital here, the electron is just spinning in this kind of plane here. And so our probability is really hard to know precisely where the electron is. It's just somewhere in those regions there. What I'm going to try to understand when we start to look at multi-electron atoms, once we, probably several slides from now start to put this together to look at configurations for things like titanium or whatever, we'll start to really try to think about how the atoms are just trying to find a way to use space. Like the real idea is if you're an atom and you're trying to distribute your electrons, it's kind of like, where do I want to put them? Do I want to put them all in S orbitals? Do I want to use some of these P orbitals? We'll start to see the D orbitals are kind of in between of the P orbitals. That'll make a little bit more sense later. But the orbitals are really just trying to deal with the idea that electrons repel each other, but they are attracted to the nucleus. So electrons are negatively charged, obviously. Nucleus is positive. So the whole reason the electrons even exist or try to spin around the nucleus is because of that negative positive attractive force. But then they have the repulsion from each other. So they're really trying to get away from each other as best as they can too. F-shaped orbitals just have 3 sets of lobes. We'll see a couple of pictures of those later. If we don't really ever even get into classifying G, H orbitals that are of this higher L value. I just wanted to kind of point out that you could have orbitals designated with those L values, and we don't really show you those shapes because they get pretty complicated. And so another quantum number, there's 4 total quantum numbers, and sort of the idea is that they relate to the size, they relate to the shape of the orbital. The third one relates to like the projection or the orientation of the orbital, sort of like where does that orbital point and how many different directions can it point is coming from the magnetic quantum number symbolized by the M sub L. And so we go N, L, M sub L, so this is an M, sub L. And then the range of the M sub L values, it goes from whatever the L value is, negative through 0 to the positive L value with all integers in between. So for example, if we have n equals 1, the range of L values is only 0 because the max L can be is n minus 1. So if n is 1, the greatest L can possibly be is 0 because that's what n minus 1. So 1 minus 1 is 0. And so this is the only possible L value. And so what this is saying is that's a 1s orbital, so 1 from the n value. and then s from the L equals 0. So like the 1s designation or the 1s orbital, it turns out there's only one projection of that orbital because the range of the m sub l's goes from minus L to plus L. So for this orbital, that's just 0. And so that tells you if you have like a spherical orbital, there's no directionality to it. You know what I mean? Like it's like a perfectly symmetrical orbital if there's no different way you can orient it in three-dimensional space. So there's only one projection of that orbital. So there's just one 1s orbital. And then that's why the first row of the periodic table, we have two elements. And the two elements, hydrogen and helium. Hydrogen puts one electron into that orbital, and then helium can put a second electron into the orbital. And now the whole idea of like spin up, spin down is coming from the fourth quantum number, the magnetic spin quantum number. This is the spin up, spin down. The m sub s quantum number is the electron can have a spin of plus a half or minus a half. And that this is telling us that each one of those orbitals that are being designated by an n, l, and an m sub l can have 2 electrons maximum. And so this rule here is telling us that each orbital that we can sort of write or come up with through a combination of n, l, and m sub l can only take on a maximum of 2 electrons. And if they do take 2 electrons, one has to be up, the other has to be down. Pauli exclusion principles, an interesting idea that 2 electrons can't share the same set of 4 quantum numbers, because that would mean that they're occupying the exact same space as each other. And electrons repel, so they don't want to be right on top of each other. Like if you have 2 electrons in a 1s orbital, one's going to be spinning kind of in one direction, the other's going to be spinning the opposite direction. You just have these 2 electrons just spinning around the atom in opposite directions so that they're not really, quote unquote, bumping into each other when they're spinning around the atom. And so magnetic spin plus or minus a half for that quantum number. Now, it takes a little bit to kind of put this all together. And also, we're going to see that we get the periodic table to sort of work its way out of this process, too. We're going to end up seeing that we end up with blocks of 2 elements that look like our S block, lithium, beryllium on downward, have 2 elements across. That's kind of what we call an S block, and that's going to look like they're filling into S orbitals. We're going to see that we get P orbitals filling 6 across. So why do the p orbitals go 6 across? Well, let's look at n equals 2. When n is equal to 2, L can be equal to 0 or 1. And so let's look at these kind of separately here. Let's look at L equals 0 versus L equals 1. And so what the L equals 0 is referring to is the 2s subshell. And then L1 and 2, that's referring to the 2p subshell, because L1's p-shape. And the number in front is just the n value, so this is just the n value here. And so the 2p set of orbitals have a range of m sub l's of -1 to 0 to +1. So 1, 2, 3, 2p orbitals. But the m sub l for L equals 0 is just 0. And so what this is telling us, like kind of right away, is that there's one 2s orbital. And so the 2s orbital can take on 2 electrons maximum. So that turns out to be lithium and beryllium, going from a 1s2, 2s1, 1s2, 2s2. We'll see configurations in a minute. But you can sort of start to see that, say, beryllium, in terms of a configuration, we put 2 electrons into a 1s orbital, then we put 2 electrons into a 2s orbital, because beryllium has 4 electrons, 4th element, and it's filling its electrons into the smallest orbital, and then the next biggest orbital. And so then what comes after beryllium on the periodic table? Boron, carbon, nitrogen, oxygen, fluorine, and neon. Well, 6 across kind of starts to make sense here because I have 3 orbitals. And so I have 3 orbitals here, 1, 2, 3 for my 2p subshell. So we start to use a lot of vocabulary kind of simultaneous to like the periodic table and some of the ideas that we're pulling from it. So we start to say things like shell. Like an n value is a shell. So n equals 1 is a shell, n equals 2 is a shell. N equals 1 shell is really small, it's just 1 orbital. So the n equals 1 shell is just that one 1s orbital. The whole 1s could be called a subshell, which doesn't mean much for like an s subshell because it's just 1 orbital. When I look at the 2p, this is what I would call a subshell. So it's part of the n equals 2 shell. So the n equals 2 shell would be the 2s and the 2p set orbitals. So the 2s subshell, again, just 1 orbital, but it's the 2s subshell and the 2p subshell. And then I start putting electrons in for boron. I just add an electron to the 2p. So boron's configuration would look like, for 5 electrons, a 1s2, 2s2, and a 2p1. Carbon just looks like the next one down, 1s2, 2s2, one more electron into 2p subshell, 2p2. So the electrons in the subshell are kind of noted as a superscript. So how many electrons are in that subshell? The 2p can get up to 6. So if I go to nitrogen, 1s2, 2s2, 2p3. And we're going to quickly see that we're using a lot of ideas simultaneous that we're going to go back through and look at in more fine detail. But as we're going to boron, to carbon, looks like this configuration, to then nitrogen, looks like this configuration. Now, how do I know how to put those electrons in that particular order? Well, we call that Hund's rule. And Hund's rule, and I often say that it must be nice to have been a really old physicist and a long time ago to think of something that would be probably pretty obvious. And like, let's think of what we're meaning by even the projections of these orbitals and how we might use them if we're an atom. And so we have a p orbital that looks like this. And so we're picturing here, if we're filling into, say, nitrogen and trying to come up with what nitrogen might look like. So we have, around its nucleus, we have a 1s subshell with 2 electrons. So we have 2 electrons kind of spinning around that subshell. If you think of one spinning counterclockwise and another spinning clockwise, you'll kind of quickly see that the arrows look like they're pointing in the same direction, but those are opposite spins. So they both look like they're spin up, but really one spinning one direction, the other the opposite direction. And so that's kind of what it looks like to have the spin up, spin down combination in the 1s. Then we do the 2s with the same idea, so each 2 electrons spinning opposite direction. And then think about how one of the orbitals starts to look like this, and you see why the orbital looks like that, is that we're trying to use like the 2p orbitals using this space here and here. Yes? Like so that the 2 little like arrows. Yeah, so that's meant to imply, like each arrow is meant to imply an electron. And so if there's, and let me even write these little symbols in here to show the 1s2, 2s2. It's meant to imply that one electron spin up, the other spin down. Yeah. And so the idea of the p orbitals, it's like we have electrons here and here. We can't really pack more electrons into that region. But we have the region here that's available. And so you start to see that the 2p subshell is using a lot of the space that's just a little bit bigger than the n equals 2 shell. And then we have sort of in 2 planes, we have, if we call one of these the x plane, one of these the y plane, and the z plane kind of going into the atom, we can see that we end up with what we call the px, the 2px, the 2py, and the one not being shown here is the 2pz orbital. And that if you're an electron, you're going to probably say, do I want to put 2 electrons into the same orbital, or do I want to use all 3 of those orbitals? It'd probably make sense to use all 3 to spread out the charge, because again, all the electrons in those orbitals repel each other. And so we call that maximizing spin. We'll see this defined on the slide a little bit later. But Hund's rule is maximizing the spin, and it really just maximizes the space that we're using to minimize electron repulsion. And so the idea of Hund's rule, I think, is actually pretty simple when you think of electrons just trying to want to maximize their use of space, their minimization of their repulsion with each other. And if we continue across to oxygen, fluorine, neon, oxygen just goes to 2p4, so we have to add another electron. If we go to fluorine, a 2p5, so we add another electron. And then to neon, we cap off that subshell. And so the thing that makes noble gases and so stable in terms of existing as a monoatomic atom, and then the atom having a weak repulsion so that things just exist as gases at room temperature, is that we've capped off the subshell. We have a completely filled subshell of electrons. So we have an atom that really is happy in terms of its electron configuration. It doesn't really need to exchange electrons with another atom to gain more stability. It's kind of just as stable as it ever wanted to be by capping off a subshell. And so what we see with like fluorine, if you kick one of these electrons back off for fluorine, fluorine has like a big gap. It has like a spot for an extra electron, and it's going to try to like fill that by taking an electron from something else. And so you can start to understand a lot of properties of atoms. Like if you go to Lithium has that one extra electron it can lose more easily to go to a more stable or a configuration that allows it to then have a greater attractive force with the net result. So we start to, like later in the class, in chapter 8, we'll get into making plus and minus ions, their attraction together, but a big idea will be the atoms that can most easily lose an electron, the atoms that can most happily accept an electron, make those charges, and they get a strong attractive force in return. Okay, so thinking of neon here, spin filling. So let's move on to, let's look at each quantum number kind of separately again, try to understand what these quantum numbers are referring to. So again, the angular momentum quantum number is defining the shape of the orbital, and the range of values for L go from 0. So N can't be 0, but L starts at 0. So the first possible value for L is 0, all the way up to N minus 1. And so if we go through another example, if we have N equals 3, then the range of L values can be 0, 1, or 2. Obviously can't be 3 because the max is N minus 1. And then for N equals 3, we'd have the possibility of having the L-shaped orbital of S, P, and D. So we could have a 3S, a 3P, and a 3D subshell within the N equals 3 shell. So we're just seeing that kind of vocabulary, that the entire N equals 3, we call that a shell. And then everything comprised of just the 3S or the 3D or the 3P, those are individual subshells. Okay, and so these are defining the shape. We'll see some shapes on our slides in a couple slides from now still. The magnetic quantum number range, again, minus L to L all the way through 0. And so if we go to the N equals 3 orbital where L is equal to 2, so that's that 3D subshell. So this is our 3D subshell. And so then the range of M sub L's here for this subshell would range from minus 2 to minus 1 to 0 to plus 1 to plus 2. So that's 1, 2, 3, 4, 5 values. So that's telling us our 3D subshell has 5 orbitals available. And each orbital can take 2 electrons. And so this is 10 electrons max into the 3D subshell. And so that's why we have blocks of elements that transition metals are 10 elements across. So we're going to see the transition metals are filling their electrons into D subshells as their last subshells that they're putting electrons into. And then we'll later see that when we get into F orbitals, there's 7 possible F orbitals for an F subshell. If we go to N equals 4, that's the first time we can have an L of 3. So you have an N4 and L3. You could also have, don't get too confused that L could be 0 or 1 or 2. So the idea of the N and L combination is they're defining a subshell. And so the N equals 4 shell, we know that there could be a 4S, a 4P, a 4D, and now a 4F subshell. And so for the 4F subshell, the range of the M sub L value would go minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. So that's how we get 7. So for any subshell of an atom, there can be up to 1 s orbital. There can be 3 p orbitals within that subshell. So if we look at the number of orbitals that are possible, there would be 1 for the 4s, there'd be 3 for the 4p, there'd be 5 for the 4d, and there'd be 7 for the 4f. Just coming from the range of the M sub L's for the L 0, 1, 2, and 3 combinations. So one of the nice things is we kind of get the periodic table back out of this whole process, or the periodic table is closely related to the work that went into the quantum mechanics to help us understand how the system works. So let's look at some of the shapes that we get. So what we see here is N equals 1, the 1s to the 2s to the 3s. So increasing the N value increases the size of the orbital. So we're seeing that the N value is related to size. This is showing us the p orbitals. So we have, let me zoom in here. So our p orbitals, we have like a px orbital. Notice that it's on the x-axis. The py is on the y-axis. The pz is on the z-axis. Now, sometimes we get confused when we start thinking M sub L values. Does the -1 refer to, which one does the -1 refer to? Which does the 0 refer to? Which does the +1 refer to? And the answer is that's way too complicated for this class. The idea that I would want you to have is that when you see a combination, let's say n equals 2, L equals 1, so you know that's a 2p set of orbitals, that there's going to be 3 p orbitals pointing into 3 different directions on our axes. And just generally, I would know that if we show you an x-axis and there's an orbital on it, that would be the px. Okay, and so then when and so I just want us to know that there's 3 p orbitals that are all pointing in opposite directions in sort of 3-dimensional space. When we look at the d orbitals, there's 5 of them, like we mentioned before. So the first time you can have a d orbital is n3. So then that would be L2 for the 3d subshell. And so looking at the shapes of the d orbitals, they mostly look like the ones I showed on that opening slide, like 2 sets of clover leaves. And there's one that looks kind of weird that it has, through this sort of plane here, the no symmetry kind of going through the atom. And so we end up with like what we call a donut ring d orbital. And so we have 4 kind of normal-ish looking orbitals that look like the p orbitals with an extra set of lobes, and then one that has like a donut ring around it. And so this, with the shading, where you see the shading implies a greater probability of finding an electron in that region, and where you see no shading is 0 probability of finding an electron. And so this region here, these are what we call nodes. So whenever you pass through a point of no probability of finding an electron, that's like a nodal plane or a nodal point. And so we have these nodes. Like the key is seeing that there's 2 sets of nodes, and this is just coming from the L value of 2. So we get 2 nodes for these atoms. If we look back at our P shape, there's 1 node. So just 1 node for these from the L value of just 1. And so we have 1 of the nodes through the nucleus of the atom for the p orbitals, 2 for the d orbitals, and then for the f orbitals, there's going to be 3. Now these shapes here, I had to go find these in a different source. These aren't from our textbook. I really don't know why our textbook doesn't put the f orbitals into it, but maybe it's because they're kind of complicated. You can see a lot of them look like you would probably expect 3 sets of lobes. And so you get 3 sets of lobes for most of the f orbitals, and you end up with these even stranger combinations of like double donut rings. And so these are just cases where these have 3 nodes. And coming from the L value of 3. And so the F values are characterized as having the L value of 3. That's what their shape is referring to. And so these are kind of some base shapes of what F orbitals look like. You'll probably never see an F orbital again after the slide. But I just thought you should kind of see an idea of what they look like. And you can probably then appreciate why we're not going to bother showing you G, H, or I orbitals, or et cetera, because those would be way too complicated. And so then lastly, the magnetic spin quantum number, the m sub s. This is the sort of key one that's telling us for any orbital, you can either have an up or down spin. Now you would probably think the plus half is this one, the minus a half is that one, but it's really undefined. The idea would be just that if you have an orbital, there's one of one spin, the other is the opposite spin. The way it's technically defined is if you apply a magnetic field, with the field's the plus a half, against the field spin is minus a half. But that's, so that's the true meaning of plus a half, minus a half. So if you have an atom that has just 1 electron and you align a magnetic field with it, then that's plus 1/2. If you then have it opposite the magnetic field, that would be minus 1. Just to kind of give you an idea of what we mean by plus and minus a half is really just the idea of seeing that if you know one is up, the other has to be down. If one's down, the other could be up. When we start writing configurations, like for hydrogen, we often write its configuration as just a 1s1, something like this. And we often just write by default the spin up, but we could write this the other way. We can write this way. That's a perfectly equivalent way to write the configuration. So either one of those are acceptable. Just more conventionally, we tend to write it with when we have like an extra electron and we have a net spin, usually we write it up, but it doesn't have to be written up. So magnetic spin's telling us 2 electrons per orbital. And so that's coming from the m sub s quantum number. So spins of plus and minus a half. Okay, so let's put this together for some atoms. And so let's kind of obviously start from n equals 1. The range of L values is just 0. The designation is the 1s orbital. The only possible m sub L is 0. We saw this earlier. So there's just one orbital here. And so the total number of orbitals in the shell is just 1. The max number of electrons, 2 electrons per orbital, is 2. So our 1s subshell is just hydrogen, helium, 1s1, 1s2. And then when we go through n equals 2, so we have our 2s for L0 and our 2p for L1. The range of their m sub L is 0, and then minus 1, 0, 1 for the L of 1. And so we have 1 versus 3 orbitals. That's 4 total within the subshell, times 2 each is 8 electrons max within the n equals 2 shell. So when we go through n equals 3, we have the 3s, 3p, 3d. And again, I think we've kind of seen this math, but just kind of summarizing that the range of m sub L is just 0. The 3 values, minus 1, 0, 1. So we're just taking the minus of that to the plus of that, all integers between, including 0. And then taking plus and minus 2, everything in between in integers. So we get 5 values for our d orbitals. And so that's 1 plus 3 plus 5. So this sum here works out to be 9. So 9 times 2 is 18 electrons max within the n equals 3 subshell. And then if we keep going, n equals 4, 4s, 4p, 4d, 4f. And so we're just increasing from 1 to 3 to 5 to 7 orbitals. And so that's 16 total times 2, that's 32 electrons max going into that subshell. And now kind of the next question is, well, in what order do you fill these subshells? And one way, the periodic table tells us that, because that's what nature determines. Nature is going to be the one that says, okay, we have all these orbitals that are possible, and what order are we going to start placing electrons into them? Well, let's look at the order. Let's look at the way nature did this for us. The periodic table is actually telling us the kind of conclusion to that story. So before we get there, a quick question. How many electrons at most can occupy the n equals 3 shell? So again, the n equals 3 shell is everything in n equals 3, so that's L0, L1, L2, but not L3, because the max L can be is n minus 1. And so that's the 3p, 3d, excuse me, the 3s, 3p, and the 3d subshells. So 1, 3, and 5. And so do we see how we can maximally put 2, 6 more, 10 more? And so that's going to be 18 total electrons. Okay, so let's look at this question here. Let me throw this to you guys here. So for an electron in a 3p subshell, what's its range of possible m sub L values? So take a minute on this one. Anybody think they have a quick answer for this one? Did you say B? D, yeah, D's right. So the range is just from this value here, minus 1, 0, plus 1. The only reason I like to ask this question here at this point is just to kind of go back to the whole idea, like you might be sitting thinking, well, can't L be 2? And if it's 2, then it's minus 2, minus 1, 0, 1, 2. Like, why is this answer wrong here? And it's because that's just a different subshell. So if you say L is 2 and N is 3, it's possible to have this L value, but that's not the 3p subshell, that's a 3d subshell. So the 3d subshell has the range of values that are shown in B. The 3p subshell has these values here. So let's think of how these orbitals look in terms of the way they use space around them in terms of sort of thinking if you plot from the nucleus of the atom outward, like where is the space being used? Most probably within some different subshells. And so if you look at an s orbital, it kind of looks like this. We have the shading here. It's, so the probability of finding the electron is going to peak sort of in this region here and then peter out as we get further away from the nucleus. And so our 1s subshell has a radial distribution. So a radial distribution function means you're kind of looking from the nucleus of the atom out along the radius of the atom. Where is the probability maximally of finding the electron? And it's really close to the nucleus, of course, for a 1s electron. And so then the thing that becomes a little bit interesting is if you go to a 2s subshell, that you have a nodal point along the axis of the atom. And so what that would look like is if you're kind of picturing this atom here for the n equals 2, and you're thinking of the shading, it's almost like you have a shading closer to the nucleus, and then a shading a little further away from the nucleus, and then there's a nodal plane in the middle, so that what you get is something that looks like you have a nodal point, a point of 0 probability pop up. And so now you might get a little confused and see that you start at 0 at the nucleus, but that just means at the nucleus has a relatively low probability, being further away from the nucleus, a greater probability. So for the n equals 2, we have one radial node. Now this is a different type of node than the like L equals 0 versus 1 versus 2 nodes. Those are like planar nodes through the nucleus of the atom. These are nodes along the radius. So these are like almost thinking you have an inner chunk and an outer chunk of a 2s orbital, and somewhere in between those orbitals is a point of no probability. And so if you then move to the 3s orbital, then we have two of these nodes. So we have two nodes here and here that are then becoming further away from the nucleus as we go up in n value. And then also the overall probability shifting to be further away from the nucleus. Now, one of the main lessons here, I think, is that when you start to look at something like, say, sodium, we'll get the sodium's configuration in a minute, but I think we can hopefully appreciate that it's a 1s2, 2s2, 2p6, 3s1. If you start looking at like a 3s orbital, that there's still some probability that that electron has of being relatively close to the nucleus. So as the n value goes up, it's not like the distribution is just shifting away from the nucleus. We still have some probability of being relatively close to the nucleus. And then oddly, these silly nodes kind of in the middle. To be quite honest, I don't know why these nodes matter, but they do like to ask this on test questions of like how many radial nodes does like a 5s orbital have? And it's just 1 minus that s value. It's kind of going back to the 1s has 0 radial nodes, the 2s has 1, the 3s has 2. So if we keep going, the 4s has 3, the 5s has 4. Again, I don't know why this is important, but if we're picturing a 5s orbital, it would be kind of picturing like 1, 2, 3, 4, and then there goes our main probability. So 1, 2, 3, 4 radial nodes. So this would be what a 5s orbital looks like. And again, the greatest probability, the highest peak, is coming furthest away from the nucleus, but we still have a relatively high probability of finding the electron relatively close to the nucleus. And so I think, to me, the takeaway is that even for electrons that look like they would be very far from the nucleus, there's still a good probability the electrons are relatively close to the nucleus. Okay, so let's take a look at the difference between 1s, 2p, 2s orbitals in terms of their radial distribution function. So if you're thinking, well, what does like a 2p orbital look like? Now, this is a complicated slide here because this is looking at one electron systems that are using these orbitals. It's very hard to get these orbitals for like an actual carbon atom versus a neon atom or whatever. So it looks like the 2p orbital is smaller than the 2s, but this is just an artifact of this being the only electron in an atom. Once we start filling electrons into the 2s subshell, it's going to push the 2p to be bigger than the 2s. But this is just kind of showing you that the orbitals are almost like fighting for space within each other. So these orbitals are just all trying to use space within themselves. The 2p orbital doesn't have one of those radial nodes. So if you notice the 2p orbital, no nodes on it. So the 2p orbital has 0 radial nodes. And so if we were to look at the 3p, this takes some zooming in to see on the 3p of tracking which one is the 3p, but that's this one here. And so the 3p P has one radial node. Now, they usually don't ask about radial nodes of anything other than s orbitals. But I just wanted to point out that the first time you can have like a subshell, so the first time you can have an s is 1, there's no radial nodes. The first time you can have a p is 2, so the 2p has no radial nodes. And so it's then the next one, the 3p, that would have one of those radial nodes. If we were to look at the 3D, I think this will be the last thing that we look at, 0 radial nodes, because that's the first time we can have a 3D. And again, it takes some zooming in and careful looking to see which one of these is the 3D. And maybe I should do this in a different color. So the 3D doesn't have any of those radial nodes. And so, again, to have a radial node means you have to be like the next, to have one radial node would be the second possible of the orbitals. So not 3D would be the 4D would have a radial node. Now again, I don't know why that would matter, but like I said, they do like to ask you about radial nodes, but it's usually only ever for s orbitals. And so I think there's a question here on like how many radial nodes does the radial probability distribution function, so those functions we're looking at are called radial probability functions or radial probability distribution functions. So how many radial nodes would you see for a 6s orbital? It would just be 5. So it just kind of comes back to the 1s is 0 radial nodes, and then so therefore the 6s would have 5. And I don't think they'd get into the 2p, but how many radial nodes does it show for a 2p? It would be 0. But what about, and then we come back to the concept of, well, what about the planar nodes? That's what we're determining from the L value. So the L equals 1 says that there's one planar. We can call that an angular node too. So the L value is telling you about a different type of node than what the radial nodes is telling you about. So a node is just a point of no probability, planar through the axis for the L values that are 1 or greater. So L1, 1 node, but that's, again, why you're getting this shape. 2 nodes, why you're getting a D shape. Why for L equals 3, you're getting 3 sets of lobes for most of those orbitals. And then those being a fundamentally different type of node than the radial nodes that we're seeing for things like s orbitals. Okay, so let's try, like the really goal here is to get to understanding configurations of atoms. And we've already been talking about this, how hydrogen's a 1s1, helium's a 1s2, so that's pretty straightforward. I hope that we're just filling into the n equals 1 shell with 1 versus 2 electrons. We get to lithium, 1s2, 2s1, for 2 electrons into the 1s, 1 into the 2s. We might think of configurations also relative to energy this way, of thinking how the 1s is more stable, the 2, or like lower in energy. Think about Bohr model, how n equals 2 was higher in energy. So this might be our 1s, this might be our 2s in terms of energy. So we could think of filling into diagrams like vertically. Vertically filling into diagrams makes a lot of sense, other than it's space. It's hard to space orient and draw these. But if you think of the difference between the 1s and the 2s, is the 2s is higher in energy, just like the n equals 2 is higher in energy than the n equals 1. And there's another artifact from Bohr model that you can take use of, is that the difference between the 1 and the 2 is going to be bigger than the difference between the 2 and the 3, which is going to be bigger than the 3 to 4. So as we start to go up in energy, the energy levels are going to start to have very similar values to each other. Okay, so let's go across. We already did this earlier, but this is just kind of showing us Hund's rule in action, and then let's look at the actual definition that we have here. So when filling into degenerate orbitals, degenerate is an interesting word. It's sometimes used in popular lingo, like in a negative sense, like, oh, look at these degenerates. But I don't know why, like, that definition, maybe it just means they're all the same. Because when we see degenerate, or when I see degenerate in chemistry sense, I think it means the same energy orbitals. And so when I'm filling into orbitals that are exactly the same in energy, the lowest energy configuration is attained when the number of electrons having the same spin is maximized. Okay, so let's take a look here. So we go from lithium, 2s1, to beryllium, 2s2, to boron, 2p1, to carbon. Is the first time Hund's rule is applied is with carbon, where I have a 2p2, and I have 3p orbitals. Let's think of it this way here. So in terms of vertical energies, I might have my 1s, 2s, and my 2p, and I'm filling 2 here, 2 here. And the question really becomes this, like, what do I do this? No, because that violates Pauli exclusion principle. 2 electrons can't have the same set of quantum numbers, so that's a Pauli exclusion principle violation. Can I do this? Well, that's not maximizing the spin. That's putting 2 electrons into the same space as each other. Probably better if I use 2 different p orbitals. So if I'm thinking of why Hund's rule is the way it is, it's probably I'm using the s orbitals, the other s orbital. One I use one p orbital, one I use the other p orbital, put those electrons further away from each other. And then why don't I, in the process, maximize the spin? So how about we do this? So when filling into equal energy orbitals, these 3 orbitals relative to each other have the same energy. So when filling into degenerate orbitals, the lowest energy is attained when the number of electrons having the same spin is maximized. And so we maximize the spin here. If I go to nitrogen, 3 electrons, maximizing the spin with 3 electrons in the same direction. And so nitrogen just puts 1 more electron into here. And if I get to oxygen, I just have to start pairing the spins because I have no other choice to fill this orbital with 6 before I move on to the next subshell. And so I get to neon, I cap off the n equals 2 shell, 10 total electrons into the subshell. I can write the configuration 1s2, 2s2, 2p6. And then sodium, as I was like hand waving through this earlier, has that configuration of neon plus the 3s1. So a lot of times we'll write configurations this way, neon 3s1, to say it's whatever the configuration is of neon plus the 3s1. And so sometimes we call it a condensed configuration where we're just saying relative to some other atom, everything of that atom's configuration, then followed by what comes next. And so this is kind of the vertical diagram showing us the relative energies for some different subshells. And so now, notice once we get across the 3p subshell, so if we're just looking at the periodic table, we go from sodium to magnesium, 3s1, 3s2. We go aluminum across to argon, that's filling 3p1, 3p2, 3p3, across the 3p6 for argon. So once we get across argon, we then kind of have a question of, well, would you go to the D next or would you go to the S next? And there's a couple principles that could be used. One that we used to teach that's not in the book anymore that you may recall learning about, it's called the off-bow principle. Does anybody happen to recall learning that? Some high schools, I think, still teach it. But the off-bow principle has a weird way that it kind of uses this approach here that only works because it works. Like there's no empirical reason why this would work. But you just kind of write out all the subshells that are possible. I could keep going past 5F, but I'm not going to have to. So it kind of says you fill 1s first, then 2s, then 2p, then 3s. That's kind of the same order we were filling in. So it's like 1s2, 2s2, 2p6, then 3s2, then we fill across to the 3p, then we go 4s. Now, if you can think of doing this, I think we can also think of just looking at the periodic table and saying, well, what comes after argon? Potassium and calcium. Those happen to be in the block of 2 elements. That's what we call the S block. And so it's the S block because it's going to come next in terms of relative energy. And so the S block is always going to come after the P subshell once we fill it in. So the next S block is filled into. And so then we will fill into the 3D subshell. Now you can see that either in terms of this diagram that I've drawn, or you can just look at the periodic table and see I have 10 across, it has to be a D subshell. So we're going to go from the 4S into the 3D. And so then if I'm thinking of coming up with a configuration for something like, say, calcium, so calcium's configuration, I can write this. If I go complete from start, this is maybe a little boring, but let's just do this at least once. 1s2, 2s2, 2p6. If I get lost, I'm literally just following the periodic table. 2 across, 2 across, 6 across, 2 across, 6 across. So I go then 3s2, 3p6, and then followed by a 4s2. And then all of this we could say is argon. So we could call it also argon 4s2. Obviously it's a lot easier to call it argon 4s2 or to write that out. But I want to make sure we understand what argon's configuration is so we understand what we mean when we write argon 4s2. Now, what about titanium? So titanium is just 2 more across. It's just element 22. So I should have 22 electrons distributed or shown. So let's call this argon, 4s2, and then we're just filling into the next subshell 3d. And I know it's a D because it's just like 10 across. I'm just like using the thought of the periodic table to kind of tell me, well, if there's 10 elements across, we got to be filling those into a D subshell. And so titanium becomes a 3d2. If we go all the way to zinc, zinc should be an argon, 4s2, 3d10. Zinc being all the way at the end. I should point out maybe where it is first, but zinc's 10 across the D subshell, so that's why it's a 3d10. Now let's do a quick double check. Argon has 18 electrons, plus 2, that's 22 for titanium, element 22. Zinc is element 30, and so we have 18 from the argon configuration, plus 2, plus 10, so that's 30. So you can always like double check the electrons you've assigned versus the electrons that should be contained within one atom from the periodic table. So just remember the atomic number for zinc is 30. So 30 protons, 30 electrons in a neutral zinc atom. Okay, if we continue past zinc, 4p. If we continue past the 4p, 5s. So we just kind of continue along using the periodic table as our guidepost. And so we just kind of did this configuration for titanium. Let's rewrite the argon, 4s2, 3d2. And let's also talk about why that's not a 4d2. So something that you could be confused by is like, how did we go from 4s back to 3 if we're in the 4th row of the periodic table? And the answer is, well, the 3d subshell is just being filled into next. It just happens to be within the 4th row of the periodic table that we finally get to it. Okay, so the reason why this is a 3D is because the first time we can have that L value is the N3L2. Okay, so the row that we're filling into doesn't relate to all the N values for the orbitals. So N3, even though we're in the 4th row of the periodic table. How many unpaired electrons? This is a very popular question for us because it's going to test if we know how to fill electrons into our diagram. So think of it this way. You have your 4s, and then your 3D set of orbitals higher in energy. So we fill 2 into the 4s, so that's our 4s2. And then how do we fill into the 3D set? Maximize the spin. So we should have 2 unpaired electrons. On Friday, we'll see something that the electrons can take on sometimes a different configuration than we expect. And I want us to try to comprehend one thing about that here, which is the 4s and the 3d start to get relatively close in energy, but not so close that we're exchanging electrons just all the time. A few elements, really, I think just one in the D subshell, the 3D subshell does this. So there's only one example of these anomalies in the first row of the periodic table, or maybe 2. But when we look at a given atom, we don't start exchanging these electrons unless we have one of those few anomalies. So just know, once we see anomalies, you may then come back to a configuration like this and say, do I need to promote those 4s orbitals to a D subshell? No, we leave them there. 4s2, electrons are spin paired. 3d, we maximize the spin for those 2 electrons. So we have 2 unpaired electrons. And what that means is I have these 2 electrons that aren't paired up in terms of their spin. The reason why that's kind of important is experimentally, you can determine the number of unpaired electrons for an atom, and then you can verify that the atom really does have these 2 unpaired electrons, as we're suspecting here. Now let's also talk about another detail. This is for a gaseous atom. These configurations aren't necessarily those that you'll see within a metallic piece of the element. This is just for looking at an isolated atom in the gas phase. So if you look at one atom of titanium, it has this particular configuration. How many valence electrons? So valence electrons, we tend to think of these as being the outermost electrons. And it's actually a complicated process because we tend to think of it as being the outermost or the most important electrons to understand for the atom. And it's going to be these 2 electrons added together for 4 total electrons. And so how do we come up with a rule for valence electrons that makes any kind of sense? So the way that we can think of our valence electrons, it's all the electrons in the outermost shell which is for this atom n equals 4, and then plus all electrons in a lower unfilled subshell. And so the 3D subshell is not the outermost n value anymore. It's n3, not n4, but it's unfilled, so we count those two. I don't think you're going to see too much questions on the test on valence electrons. It's something that us instructors kind of argue about the importance of talking about this in this chapter, but it's something that does come up in the chapter, and it's something that later on we'll be building from. So I wouldn't be overly concerned about questions that get at valence electrons, because it is a complicated question. It's something we do build more from in later chapters. So we'll get into some bigger atoms next time, wrap up chapter 6, and start to get into a little bit of review on Friday ahead of next Tuesday's exam. I'll have that 7:15 review session before class on Monday, just to make sure that's on your radar. Friday night review by Dr. Wynn. I'll resend an announcement on that, but her review is Friday this week for midterm 3. So earlier announcement, I'll resend that soon, just in case you need the info. All right, guys, have a great day.